In this lesson, we're going to learn how we can use the probability of an event to make a prediction. There are two different types of probabilities that we're going to be using to help us make predictions, and we're going to start off with theoretical probability. The theoretical probability of an event is the mathematical ratio of the number of possibilities in the event over the total number of possibilities. This type of probability represents what should happen when you're conducting an experiment. Okay, now once we know that probability, we can use that to make a prediction. If you know the probability of an event, you can predict the results for a large number of trials. In our first example, we have a spinner here, and it says when spinning, the fair spinner shown here, you would expect in theory to spin an odd number 3/8 of the time. Okay, we can see by looking at the spinner, there's 8 total sections, and there are 3 odd numbers, 1, 3, and 5. All the other numbers are even. Okay, so the probability of landing on an odd number for the spinner is 3/8. In theory, if you spin the spinner 104 times, an odd number should appear how many times? That's what we're interested in figuring out. How many times are we going to land on an odd number? So what we're going to do is use the probability of landing on an odd number to figure out this prediction. We're going to use a ratio, since probability is a ratio, and we're going to set this up as the number of odds in the numerator over the total in the denominator. Okay, now for this spinner, there are 3 odd numbers, the 1, the 3, and the 5, out of the total 8 sections. This is why the probability of landing on an odd number is 3 out of 8. We can take this ratio and set it equal to another ratio where the total number of times we're spinning the spinner is 104 times. We have to figure out how many odd numbers are going to appear out of the 104 tries based off of this probability. Since we know both denominators, we should figure out how we scale from 8 up to 104. Okay, well, if you did a division, 104 divided by 8, that would give you an answer of 13. So to go from 8 to 104, you had to multiply by 13, which means we'll do the same thing in the numerator. 3 times 13 is equal to 39. Okay, so this means that an odd number should appear 39 times in 104 spins. Okay, so our prediction, if we were to spin the spinner 104 times, our prediction is that we would get an odd number 39 times. And again, this is based off of the probability of 3/8 landing on an odd number. In theory, this is what should happen. In our second example, we're going to use a die to make some predictions. Letter A says, if you roll a die 108 times, how many times would you expect or predict to roll a 5? Okay, so we're going to need to know the probability of rolling a 5 on a die in order to help us make that prediction. So the way that we're going to set up our ratios, okay, we need to know the number of 5s that are on a die. And again, in our denominator, we need to know how many total numbers there are. Well, on a die, there's only 1 5 out of the 6 sides. So the probability of rolling a 5 when you roll a die is 1 out of 6. Based off of this probability, we're going to set this equal to another ratio where the total represents how many times we're rolling it, and in this case, that's 108 times. We have to figure out how would we scale from 6 up to 108. So if we do 108 divided by 6, that's going to give us an answer of 18. So to go from a 6 to a 108, we must have multiplied by 18. If we do the same thing in the numerator, times 18, that's going to give us exactly 18. Okay, so this means that you should roll a 5 18 times in 108 tries. Okay, so that's our prediction. Out of 108 rolls of the die, we should get a number 5 18 times. In part B, it says that if you roll a die 342 times, how many times would you expect or predict to roll a prime number? Okay, so again, we're going to need to know the probability of getting a prime number when you roll a die. Let's set up our ratios as the number of primes on a die over the total. Okay, well, for the total, again, we know there's 6 sides. And on a die, the prime numbers, remember, a prime number is a number with only 2 factors, one in itself. Okay, the prime numbers on the die are 2, 3, and 5. So 3 of the 6 sides are prime numbers. So the probability of getting a prime number on the die is 3 out of 6. We're going to set this equal to another ratio where the total number of rolls is 342. And again, we have to figure out how are we going to scale from 6 to 342. So if we do 342 divided by 6, that's going to equal 57. Okay, so we must have multiplied 6 by 57 in order to get to 342, which means we're going to have to do the same thing in the numerator. 3 times 57. And if we do that multiplication, that gets us 171. Okay, so this means that you should roll a prime number 171 times in 342 attempts. Okay, so there's your prediction. When you roll a die 342 times, you should get 171 prime numbers. In example 3, we're going to use the probabilities from spinning this spinner with 4 sections in order to help us make predictions. In question A, it says if you spin the spinner 144 times, how many times would you expect to spin a green? Okay, so we need to know what the probability is for landing on green in order to make that prediction. So when we set up our ratios, we're going to do the number of green sections out of the total spinner. Okay, so we know the spinner has 4 sections. That's our denominator. And for the number of greens, well, only one of the 4 is green. So the probability of landing on green is 1/4. And we're going to set this equal to another ratio where we're spinning the spinner a total of 144 times. We need to figure out how to scale from 4 up to 144. So we should do 144 divided by 4, and that's going to equal 36. So 4 times 36 is 144. Do the same thing in the numerator. 1 times 36 is 36. And so this means that you should land on green. You should land on green 36 times in 144 attempts. Okay, so that is our prediction. 36 greens in 144 attempts. In question B, it says if you spin the spinner 96 times, how many times do you expect to spin a primary color? So we need to, again, figure out the probability of landing on a primary color. So let's set up our ratio as the number of primary colors over the total spinner. And again, the spinner has 4 sections for the total. The number of primary colors. Well, the primary colors on this spinner are blue, red, and yellow. So that's 3 out of the 4. Our probability of getting a primary color is 3/4. We're going to set this equal to a ratio where the denominator, we're spinning it 96 times in total. So let's figure out how to scale here. 4 up to 96. 96 divided by 4. Well, that's going to be equal to 24. So we must have done 4 times 24 to get to 96. In the numerator, we're going to do 3 times 24, and that's going to give us an answer of 72. Okay, so this means that you should land on a primary color. You should land on a primary color 72 times in 96 attempts. Okay, so it's very important to get that initial probability for the event in order to make your prediction. So in the last few examples, we used theoretical probability in order to make our predictions. And again, theoretical probability is what should happen. Experimental probability is a probability based on the number of times an event happens when repeating an experiment a large number of trials. This is also called empirical probability. This represents what actually happened when an experiment has been conducted. Experimental probability will approach the theoretical probability after a large number of trials. Okay, so the more and more times that you conduct an experiment, all right, the probabilities are going to approach the theoretical probability, which again is what should happen. Okay, in the next few examples, we're going to be using experimental probability in order to make our predictions. In question 4, it says in a school, 45 out of 60 students said that they would go to the student council dance on Friday. If there are 720 students in CODA, how many students should be expected at the dance? Okay, so what they did here, instead of asking all 720 students that go to CODA, they asked a smaller portion of 60 students who were going to go to the dance, and 45 said that they would go to the dance. So we're going to use that probability to predict how many are going to go to the dance. So let's set up our ratio as the number of students that are going to the dance out of the total. Okay, in our small experiment of asking 60 students, all right, our total was 60 students and 45 said that they were going. So the probability that someone's going to the dance is 45 out of 60. We're going to use that probability and set it equal to another ratio where the total represents how many students are in CODA, which is 720. We have to figure out, how did you scale from 60 up to 720? So we're going to take 720 and divide it by 60. And when we do that, that gets us an answer of 12. So we did 60 times 12 to get up to 720, which means we need to do the same thing in the numerator. 45 times 12, that gives us a value of 540. So this means that about 540 students should be expected to attend the dance. Okay, and again, this is just a prediction that we've made based off of the experimental probability of asking 60 students. 45 out of the 60 students said that they were going, so now we're going to predict out of the entire CODA Middle School, 720 students, that 540 students should be expected at the dance. In example 5, a survey of 200 people was taken, and 120 said that they would attend a concert in the park. If there are 16,000 people in the town, how many people are predicted to attend the concert? Okay, so this is very similar to the example that we just did. We want to predict how many people are going to the concert. So let's set up our ratio again as the number that are going over the total. Now, again, we didn't ask all 16,000 people. That would be very tough to do. We've asked a smaller group of 200 people. So our total number of people in our experiment was 200 people. And the number of that were going out of those 200 was 120. So we're going to use the probability of 120 over 200 that somebody is going to the concert and set that equal to another ratio where the total number is the town of 16,000 people. How did you scale from 200 up to 16,000? Well, let's do 16,000 divided by 200, and that's going to equal 80. So 200 times 80 is 16,000. We'll do the same thing now in our numerator, 120 times 80, and that's going to give us 9,600. So this means that about 9,600 people should be expected to attend the concert. Okay, that's our prediction. Out of the entire town of 16,000 people, we're predicting about 9,600 people to attend the concert. In example 6, they tell us that in Bill's homeroom, 13 out of 30 students voted for him. How many do you expect to vote for Bill out of the remaining 90 students on his team? Okay, so Bill is running for some sort of class office and he wants to predict how many votes he will get. So let's write down our ratio as the number of votes for Bill out of the total. Okay, so in Bill's homeroom, there's only 30 students. That's the total number. And 13 of those students voted for him. So the probability that someone's going to vote for Bill is 13 out of 30. We're going to make our prediction now for the total 90 students that are left on his team. How many are going to vote for him? So we have to figure out how to scale from 30 up to 90. And that's an easy scale. 30 times 3 is 90. So we'll do the same thing in the numerator, 13 times 3, and that is going to equal 39. Okay, so we can say that Bill should expect about 39 more votes from the students on his team. Okay, so again, based off of the experimental probability where 13 out of the 30 students in his homeroom voted for him, we're predicting 39 out of the remaining 90 students to vote for Bill as well. In example number 7, it says that 45% of the students surveyed said that they want candy sold in the cafeteria during lunch. There were 180 students surveyed. How many of them would you predict would want candy sold during lunch? Okay, so notice here that they've given us the results as a percentage, okay, 45%. We're going to set this up as a ratio where the numerator is the number that want candy, and again, the denominator is always your total. And for a percentage, we know that the total is always 100. And based off of this survey, 45% or 45 out of 100 students want candy. We're going to set this equal to another ratio where the denominator represents the 180 students that were surveyed. And we have to calculate how to scale from 100 up to 180. So if we do 180 divided by 100, well, that's just 1 and 8 tenths. So we multiplied 100 by 1 and 8 tenths. We'll do the same thing in the numerator, 45 times 1 and 8 tenths. And that's going to give us a numerator of 81. So we're going to say that around 81 students want candy sold during lunch. Okay, so again, that was based off of the experimental probability from the survey where 45% wanted candy served. In example number 8, Marty took a survey of 48 out of 200 students in the 7th grade to see if they were going on a summer vacation. 30 of the students said that they were going on a summer vacation. What is a good prediction of the number of 7th grade students who are going to go on a summer vacation? Okay, so let's think about how we should set up our ratios. In the numerator, we're going to put the number that are going to go on vacation. And the denominator, of course, is our total number. All right, so Marty surveyed 48 out of the 200 students in the 7th grade. He didn't survey all 200 of them. He only surveyed 48 of them. So 48 represents the total that Marty surveyed. And out of those 48 students, 30 said that they were going to go on a summer vacation. So the probability that someone's going on a summer vacation is 38 out of 40. We're going to set that equal to another ratio where the denominator represents the total number of students, which in this case is 200. And we have to predict out of those 200 how many are going to go on summer vacation. So once again, we have to figure out how to scale from 48 up to 200. So if we figure that out here, we're going to do 200 divided by 48. All right, and if you do 200 divided by 48, well, notice here that you get that decimal of 4 and 1600ths with the 6 repeating. All right, times 4 and 1600ths with the 6 repeating. All right, don't clear that number off of your calculator, okay, because you're going to need that number for the numerator when you do your multiplication. We're going to multiply 30 by 4 and 1600ths with the 6 repeated. So keep that number on your calculator, and now just hit times 30. And notice that we get a nice 125 here. Okay, so that this means that around 125 seventh graders will go on a summer vacation. Okay, so again, this is just our prediction based off of the survey that we did. Okay, we're predicting that about 125 seventh graders will go on a summer vacation.